Houston, I'm on the porch. Roger, Neil. Neil, this is Houston, loud and clear. Break, break, Buzz, this is Houston. Radio check and verify TV circuit breaker in. That's one small step for man, one giant leap for mankind.
This has been man's greatest adventure. The most difficult, the most hazardous journey ever attempted. Flinging man out across 250,000 miles of space to a harsh, airless world, with life and death hanging on each flaming blastoff, step into vacuum, and rocket burn. And we made it. We won the race. We found a multitude of treasures. It's true. By the time the last Apollo splashed into the ocean, right on time and on target, the suspense had gone out of it. The painstaking thoroughness, the systematic skill of that whole operation had made flying to the moon seem, incredibly, the safest form of travel. But in that very operation lies one of the treasures. One that may turn out to be more important to us than all the rest. That one is here on Earth. Centered here, near Houston, in the bayou country west of Galveston Bay at the Johnson Space Center. Here, in assembling the skills that guided the moon flights, something quite special, something quite new in the world had been created. What had come about was the development of new systems for enlarging human competence. Ways of meshing together men and machines to accomplish large and difficult tasks. To attack problems at a grand scale, as complex as the problems of our expanding society. Problems of cities, of transportation, of environments, of energy. In short, an arrangement to enhance, intensify, to amplify man's capacity to do what man, at his best, does best, to make decisions, and to communicate with other men.
T-minus 17, final guidance release. We'll expect...
During the long countdown and the 3-hour hold, Apollo 17 was directed from NASA Launch Control, Cape Kennedy.
Ignition sequence started. All engines are started. We have ignition. 2, 1, 0. We have a liftoff. We have a liftoff, and it's lighting up the areas. It's just like daylight here at Kennedy Space Center as the Saturn V is moving off the pad. It has now cleared the tower.
At the moment the Saturn V booster cleared the tower, control was handed over to Houston. The spacecraft dwindled from sight and started out across the miles of space. A vast amount of information about that ship and its crew streamed back and forth between Apollo and the Manned Spacecraft Center. The torrent of data pouring into Houston was instantly sorted and processed and displayed in the Mission Control Center. Throughout the flight, a complex communications network linked controllers, ship, and crew into a close, immediate contact. This exchange of information, spacecraft to Houston and Houston to spacecraft, reached a peak during the descent to the moon's surface. Descent had been scheduled at a time when both the lunar module and the command module, having separated behind the moon, were both in line of sight of the Goldstone antenna in California.
Range is a plus 2.8. Over. Thank you, Gordy. I'll give it a final trim at 4. Okay. Oh, man, are we down among them, babe? Woo!
The telemetry data coming back was directed through the routing computer to the groups that monitor onboard systems, life support and biomedical systems, the astronauts' physical condition and environment, fuel, air, water, batteries, the spacecraft's attitude, acceleration, velocity.
53 degrees.
Continuous voice links were maintained between the spacecraft and between each craft and the capsule communicator at Houston.
Yeah.
That's affirmative, 410.
Stand by for pitch over, Jack. Pitch there it is. Proceeded. And there it is, Houston. There's Camelot. Wide on target. I see it. We got them all. 42 degrees.
The flood of information from both craft continued to flow into the displays at Mission Control, was distributed to computers for real-time calculation and prediction, and to the flight controllers and the flight director for his decision. Okay, Challenger, you are go for landing.
Peak altitude degree, you threw 800 feet. H dot's a little high. Little forward, G. Yeah, I don't need the numbers anymore. Going down at 5. Little forward a little. 90 feet. Little forward velocity. 80 feet. Going down at 3. Going down at 10. Cut the H dot. It feels good. Feels good. 20 feet. Going down at 2, 10 feet, going down about 2, very little dust, very little dust. Contact. Okay, Houston, the Challenger has landed.
Roger, Challenger, that's super.
But we is here.
When there is, finally, a moment to look back, it appears that the astounding success of the space program is rooted in a cooperation among NASA scientists and engineers and American industry. NASA and many of the major high-technology corporations in this country teamed together to supply the hardware, propulsion systems, knowledge and skill needed to put man on the moon. Philco Ford provided the telemetry and communication systems, the systems that receive the data, processed and sorted and displayed it. They also were responsible for the command and control operation, the training of people to use the networks of information channels, and the design and operation of the Mission Control Center itself.
This business of ours seems just like chasing...
This is Bob Benware, Philco Ford's Chief of Operations at the Johnson Space Center.
This thing we call telemetry, that's really three things. Sensing the data, sending it to the user, and then showing it to him. Originally, messages were sent by Morse code at 30 words per minute. And then with teletype, we got to 100 to 120 words per minute. And that's where we were with Mercury. Then with the Gemini and Apollo, we boosted that to 100,000 words per minute. It's really hard to visualize the vast amount of data coming from the moon to mission control. During his Apollo 15 moonwalk, astronaut Dave Scott performed an experiment based on an assumption of Galileo. He dropped a feather and an iron ball side by side to see if, in a vacuum, they would fall at the same rate. While they were falling, Scott's heartbeat, respiration rate, skin temperature, energy consumption, and the power supply feeding the life support systems and oxygen reserves, as well as an equal amount of data from James Irwin, his companion on the moon, were being sent out. At the same moment, the charge in the batteries on the lunar rover, the condition of both stages of the lunar lander, the multiple outputs of the scientific instruments set up on the moon's surface by these astronauts, as well as those left by all the previous astronauts, join in. And orbiting above, the command service module is adding its own package of information about astronaut Al Warden's person, environment, and the onboard systems, all of which is sensed, converted, and transmitted through space to be caught in the Goldstone antenna 250,000 miles away before the feather and ball fall together to the ground. And now for Skylab, we're processing 5 times as much data.
Believe it or not, Gordy, I'm ready for your pad.
Okay, Jack, it's a mid-course 2, SPS/GNN. Sexton star is 25.
Okay, with trimmer altitude plus 310.
Ignition time is 035.
Control power is on. Finger on the station. Okay. Woo. Man, bounces around.
It's too late. Let's break for lunch.
Wow, boy, that seemed real.
Yes, we feel the more realistic training is, the more that you will get out of it.
This is Ambrose Davis, manager of Philco's Flight Control Department in Houston.
Our job is to train flight controllers so that they can control the mission. We train them here in our crew station trainers so that they really understand the physical reality of the spacecraft. Not to ask a man who's performing an experiment on the telescope mount to throw a power switch that's down in the workshop area, for example. And before each mission, we run hundreds of hours of simulations, right in mission control. Simulations train these large groups to work as a team, and that includes the astronauts, who are in their trainers over in Building 5, and the remote sites, Goldstone, Spain, Australia, and so on. They learn voice disciplines, when and how to report in, how to handle problems and emergencies. This work, this training, builds confidence. Confidence in the equipment, that you can count on it, that the controllers can use the information they get to make decisions, so that they know when they mash a button, they're going to get the display they asked for. When they press a button to send a command, that command is going to get sent to the spacecraft. And it gives the astronauts confidence in the flight controllers, so that on flight day, the plan that we've thought out in such detail will actually work in practice.
63 seconds after the launch of the Skylab space station, at the point of maximum stress, telemetry told Houston that the unmanned spacecraft was in trouble. Over the next few hours, from the information coming down from the Skylab sensors, the flight's controllers were able to deduce that the large aluminum micrometeorite shield had torn away, which left the cylinder containing the living spaces exposed to the direct heat of the sun. Temperatures inside the craft rose to 130 degrees. The disintegrating shield had ripped off one of the solar panels and trapped the other, leaving Skylab seriously short of power. Immediately, the greatest fix in space history was begun, a heroic effort to save the Skylab mission. Here in the giant water tank at the Marshall Space Center in Alabama, the astronauts tried out schemes to restore the Skylab to usefulness. Their spacesuits waited to simulate the weightless conditions they would experience in orbit. They tested designs for sunshades that could cool the ship to livable temperatures. This is astronaut, physicist, and former Philco scientist Ed Gibson, a member of the third Skylab crew, who talks about the events that followed.
When the trouble started, our telemetry told us in detail what Pete and his crew would face. This allowed us to come up with some good solutions before they went into orbit. The deployment of a parasol, or sunshade, out of an airlock reduced the temperatures inside to a workable level.
But erecting that one remaining solar array to gain more power was a bit difficult and required a spacewalk. Pete Conrad and Joe Kerwin pulled the EVA off beautifully, and the Skylab program was back in business. It was a team effort in a very large sense. Our telemetry and the TV from our first look at the vehicle let us look over the shoulders of the guys up there. And the NASA team, with ingenuity and a lot of hard work, came up with the solutions. Some of the really interesting questions that we hope to answer on Skylab have to do with how well men can live and work in space. To help with this, there are a number of instruments that measure our physical condition, located down in the crew quarters area. As we exercise on this bicycle, measurements are made of our heart rates, of the electrical activity of our hearts in 3 dimensions, and even of the amounts of oxygen consumed and of carbon dioxide produced. Another instrument measures the quality of our sleep. All of this data is recorded and then beamed down to Mission Control in short bursts as the Skylab passes over its receiving stations. For much of this work, even though it occasionally looks like play, we will learn more about man himself. In the workshop space and up in the multiple docking adapter, we have experiments which are performed in biology and in physics and in metals technology. And also from here, we control the sophisticated Apollo telescope mount, which is designed to learn more about our primary energy source, the sun. The Apollo telescope mount carries about a ton of sensitive instruments and cameras, all aimed at the same point on the sun's surface, each one sensing a different part of the sun's rays. The red light of hydrogen, X-rays, ultraviolet, some of which can only be viewed from space, outside of the Earth's atmosphere. The telescope mount and several other experiments look at different astronomical events in the sky, including the dramatic visitor to our Christmas skies, Kohoutek's comet. Skylab studies of the comet's radiation may lead to a new understanding of these unusual bodies, as well as the nature of our solar system. Also there, in the multiple docking adapter, we have a battery of cameras and instruments, which we use to observe the Earth below.
And with these instruments, we hope to learn how to accurately survey our Earth resources from orbit, and in time, to manage, preserve, and even to a degree, replenish them for man's benefit.
Photographing the Earth from airplanes and now from space has added a new perspective to our view of the world. What is new is the use of sophisticated electronic devices which sense heat, radio, and microwaves to produce pictures of the Earth, and new films sensitive to infrared and ultraviolet light that can see through clouds and haze to give us startling pictures in which the colors, while unreal, are meaningful to the trained eye. This is a mapping of an attack of corn blight in the Midwest, taken through several consecutive months on infrared film. This area around Trinity Bay in Texas is being used as a test site for these new techniques. Here it is, viewed by film sensitive to infrared, seen by radar, scanned by a sensor that records heat. Differences in the water temperatures in the power plant's cooling pond show clearly. When the outputs from these and other sensors are brought together by a computer, they can reveal more and more information. Here in a national forest, the computer is producing an inventory of the number and types of trees. The green is pine, the red is hardwood. The imagery produced by this new field has the strange look of an alien planet. But the study of these images can give experts new insights into the nature of severe storms, the ability to predict floods and earthquakes, to map the Earth's natural resources and locate oil and needed minerals, to protect the environment, and to improve crop yield by managing water resources and controlling plant disease. Investigators work with images produced by this Philco system and other experimental systems to find ways of making the information transmitted from space useful to men on the ground. In this task, computers, remote sensors, machines, and men are linked into a system designed to extend man's senses and capabilities. A communications network, the development of which has been Philco's major contribution, tying together NASA's vast systems for handling and using data, but training and organizing people for managing projects of a complexity quite beyond any ever attempted. It amounts to a new way of going about doing things, a new tool, a treasure of the mind. Since the Greeks, men have known that the Earth is a round ball hanging in space. Even this knowledge did not prepare us for that moment when, live from the moon, we saw our cloudy sphere floating alone in blackness. Viewed from such a distance, the needs of that small planet seemed very close. On this voyage of exploration, we have discovered a treasure in the minds of men and rediscovered a world on which to spend it. The circle has been closed with the intricate arts of thought and execution that brought us to the moon. We can turn back to look at the problems and possibilities of Earth.